I am audible. So let me share my screen first. All right. So in this tutorial, we basically discuss the Monte Carlo method. Okay. And so the Monte Carlo methods are the computations algorithms that rely on repeated random number sampling, okay, to obtain the numerical results. Okay. And we use these methods, okay, to estimate that the numbers that we do not know. Okay. So in this tutorials we learn the basis of Monte Carlo simulations using Mathematica. Okay. And if you have any questions, you can unmute yourselves and ask the questions. Otherwise, you can also write an email or put in the forum. Okay. So let us first start with some necessary commands, okay, to perform the Monte Carlo simulations. Okay. So I repeat, the Monte Carlo simulations are uses random numbers. Okay. So how to generate random numbers in Mathematica? Okay. So so this is basically let us say I want to generate some random number from -1 to +1. Okay. So my range are 1D things. Okay. So that is why I choose that x min is -1 and x max is +1. Okay. Basically, I want to generate -1 to +1s. So random numbers I want to generate this. Okay. So I first run this, okay, and then I generate the random real. Okay. So this the functions that is embedded in the Mathematica, okay, that generate a number, okay, random numbers, okay, within -1 to +1. Okay. So just put x min and x max, okay, within the second bracket, okay, that is generate a numbers, okay, that is let us say -0.99. 7444, right. So this is in between -1 to 1, and then you can you recompile this, okay, you get different numbers, and every time you will get some random numbers, okay, generate from within this range, right. Now you want to generate, so this generate only one, right, but if let us say I want to generate 10 numbers, okay, 10 random numbers in between -1 to +1. Okay. So therefore, we use this random real, the same thing as before. So x min to x max, but I put 10 here, okay, because I want to generate 10 numbers from this. So if you see, the 10 random numbers are basically showing up as a list. Okay. So you can generate, let us say I want to generate 5 numbers, so you see the 5 10 numbers, okay, and all the things once you recompile again and again, it always get some different numbers, because this is the random numbers, okay, that I want to generate. Another important concept is the loops. Okay. So so there are two useful methods for doing iterative calculations in Mathematica, right. So one is the do loop, okay, and other is the while loop. Okay. So loop calculations are usually appears when you calculate something in a iterative way. Okay. So calculate things and they can go back to the previous equations and then calculate. So in this iterative way, when you calculate something, so you need some loop, okay, things. Okay. So loop process. So this loop process are performs using this do loop, okay, and other things the while loop. Okay. So do loops works well for simple and nested loop, right. So nested loop is basically just we do so let us say I calculate something and then I update to the from the beginning. Okay. So this kind of loops, okay, there is no conditions that is need to be satisfied, okay, in order to perform the loops. Okay. On the other hand, the while loop, okay, so it is useful for complex loop and is the conditional. So if you have let us say some conditions, okay, if this condition satisfies, then this loop go on, if this not, then stop, right. So this kind of loop we use while functions. Okay. So let us do some examples. So let us first do loop. Okay. So this is do, okay, so you just put do and within third bracket. So this is your 1D loop here. So, my function is f 2x plus 3, okay, and I print f, okay, and the values of x is minus 1 to 1 with a gap of 1. Okay. So, that means this loop is basically performed 3 times. Okay. First they take the values of x is minus 1 and then go to 0 and then go to 1, right, with a step of 1. So, minus 1 to 1 with a step of 1. So, that means there are 3 steps, right. That means this loop run 3 times, right. So, first times they take the values x equals to minus 1. Okay. So, it takes value x equals to minus 1. So, what is the values of f? If you put minus 1 here, so this is minus 2 and this is plus 3. So, the f value plus 1, right. So, the value of h is plus 1 and we print this value. Okay. So, f equals to the values of f is printed. Okay. And second times they use 0, right, because minus 1 and with a step of 1. So, it is 0, right. If we put 0, then the values of f is 3, okay, and one more time because I have to go up to 1. Okay. So, from 0 and then the next is 1 because the step of the step is 1. Okay. So, if we put 1 here, so this is basically 5, right. So, that means if we run this, okay, I get 3 values, f equals to 1, f equals to 3, f equals to 5, because this loop run for 3 times. Okay. So, let us say if we put 2 here, okay, how many times this loop run? It is 4 times, right, because we have to 2 count. So, that means if we put 2 here, this is basically 4 plus 3, 7. You see this loop run for 4 times and they print f equals to numbers, okay, that is 4 times. Okay. So, 1, 3, 5, 7 and so on. So, if we just put the numbers here, increase the number of things and that. So, this is the kind of simple and nested loops. Nested loops is basically if we use another loop within this one loop. Okay. So, it is kind of nested these things. Okay. So, loop and again we perform another loop within that bigger loop, okay, we perform a small loop. Okay. So, in this way we can nested this. For example, this. Okay. So, basically so this is a 2D loop. Okay. So, again I use 2 variable x and y and I print the product of the values. Okay. And also I print what is the values of x, what is the values of y. Right. So, I have a 2 variable x and y. Right. So, I run x minus 1 to 1 with a step of 1 and y minus 1 to 1 with a step of 1. So, here I do for only one variables, here I do for the 2 variables, that is why 2D loops. So, how it takes? So, first they choose x equals to minus 1 and take all y values. Okay. So, if you put x equals to minus 1 and what is the values of y then? Minus 1, 0, plus 1, similarly as before. Okay. So, if we just run this, okay. So, they calculate okay. So, they first fix at x equals to minus 1 and they take y equals to minus 1, y equals to 0, y equals to plus 1. So, these 3 for x equals to minus 1. Okay. They printed what is the values of x y, okay, x times y. Okay. For the next times they choose x equals to 0. Now, you increment x with a one step, minus 1 and then plus 1. So, it is basically 0, right, and again they take y, the values of y is 3 values of y, right, y equals to minus 1, y equals to 0, y equals to plus 1. Okay. But this loop is not end here, right, because there is a one more values. I have to go x to plus 1. Okay. So, that means this loop again run one more time. So, if we choose x equals to plus 1, again we choose y minus 1, y 0, y plus 1. So, basically this loop run 9 times. In 1D, if we just choose only one variable x, okay, so this loop run 3 times, but if you perform a 2D loops where the 2 variables are there, so this loop runs 9 times. is 3 square. So now, so this is the do loop. Now, just a minute. Okay, so now if you do a while loop, okay, suppose conditional loop, right. So I put some conditions, okay, when these conditions are met, the loop is performed, okay, otherwise this loop is stopped. Okay. So let us say I start with some initial number x is minus 0.1 and my condition are basically sin x square. Okay. So this is the conditions. Okay. Condition is basically so the sin x square less than 0.5. Let us say I use these conditions, okay, to stop the loop. Okay. So the loop is running. Okay. So when these conditions are met. Okay. So here is only one condition. So we just choose condition less than 0.5. The condition are basically sin x square. Okay. And x is I start with minus 0.1. Okay. So you have to start with some numbers. Okay. So if you put x minus 0.1, you calculate sin x square. Okay, you calculate, and if these numbers are less than 0.5, then this loop performs. So the next step in the loops is basically update the x. Okay. So I update x is basically x plus 0.5, and again I calculate the conditions. Okay. If the conditions again met, this loop is performed. Okay. So so if you run this, okay. So this is now in this conditional case I use while loop. Okay. So in this case do loops is not works. So you have to use while loop. So while loops I put some conditions and then I perform this loop. So basically in first case if you calculate x is minus 0.1, I calculate sin x square, right, and the values of sin x square is less than 0.5. Okay, so that is why this loop continue. Okay, and then I calculate x. So my x is minus 0.1 and plus 0.5. So now my updated x is basically 0.4. Okay, and so that is why they print 0.4, right, and I again calculate conditions. Okay. So if you calculate conditions, you see that the conditions is basically less than 0.5. Okay. So just check. So I calculate my condition is basically sin 0.4 square, right. So you see minus 0.159. So that is less than 0.5. The loops continue, right. So so now we again update the x. So my updated x is basically 0.4 plus 0.5, 0.9. So that is why they print 0.9. Now I calculate a sin 0.9 square, you see 0.72, right. So that is not the conditions here, right. So it fails the condition, right. So that is why this loop stop here. Okay. So that is why after 2 values of x, the loop is stopped. Okay. Because this condition is not met. Okay. So now it is clear, right. So what is the while loop and what is the do loop? Okay. How we perform a conditional loop. Okay. So be careful, because in some cases these loops actually never stop. Okay. Because if you put a conditions, okay, I mean that is always satisfied. So these loops actually running infinite times. Okay. So be aware of that fact. Okay. So the while loops may run infinite times if the conditions is always satisfied. Okay. So there is no stopping math. While is the do loop is basically we have some boundary. Okay. So I put some boundaries. Okay. After this this loop performed, but here is there is no boundaries. We just put the conditions. If the conditions are met, so the loops are basically runs forever. So this is the things you have to keep in mind. So before performing this kind of loops, okay, you first check that the conditions are somewhere these conditions are stop. Okay. Stop the loop, otherwise it's run forever. Okay. So in Mathematica, the while loops run as long as the conditions are true. That is the one criteria in this loop. So, and you can include multiple conditions using logical operators like and, or not. Okay. So logical operators basically, let's say I put two conditions. Okay. Okay. So you have to use and, right, because any of this true is not works. Okay. Both are true, then it works. So this is basically AND gate. Okay. So both of are 1, then is 1. Any of it is false, then it's 0. Okay. So let's say I start with I equals to 1. So this is initial number. So in while loop, we have to always initialize the things. Okay. You have to use the variables I. So you have to always initialize, because they start with this number. Okay. That's why, to check the conditions. Okay. So let's say I start with I equals to 1, and my conditions are I less than 20 and even qi. So this is basically if I is even, and that is false, right. So that means I print always odd I. If I is even number, then it false, right, because I set the conditions my I equals to false. Okay. That means I should be false. If I is even, then this loop stop. Okay. So now you tell me in this loop what is the output. Okay. So I start with I equals to 1 and I put these conditions. Okay. So both the conditions must be true. Okay. Otherwise this loop never run. Okay. So first case, so I start with a 1, so it's less than 20, a true, and even qi is false. Yeah, so I is odd, so even q is false, is also true, right. They print I. Okay. So print let's run this. Okay. Print I, and then I update I plus plus. So that means I plus plus means I equals to I plus 1. Okay. So if you start with 1, so the next I is 2. Okay. So if you go to again 2, so 2 less than 20 is true, but 2 is a even number, right. So it's not equals to false, right. So it's a true. Even qi is equals to false. I said this has to be false. Okay. That means my I always to be a odd number. Okay. But if I equals to 2, so this is a even number, right. So this is true. Okay, this will be true, because even q is a even number, right. I is a even number, so this will they return 2, right. But I said false. Okay. So that means these conditions are not met. Okay. So that's why this loop stops here. Okay. So you see only one print. Okay. If we start with 3, right, then they only print 3, because the next number 4 are even, right. Yeah, but it is less than 20. These conditions true, but these conditions are not true. Okay. So when one condition is false, it intermediate steps. Okay. In the intermediate steps, okay, the loop stops immediately. Okay. They are not performed anymore. Okay. This loop is not going anymore. Okay. This is stopped there. If some intermediate steps the conditions are failed, okay, they stop there. Okay. Let us do on examples. Okay. So so these examples is very good example. So I will show you later what is this example means. Okay. So let us say I have these 3 variables. Okay, n equals to 0 and my estimates also 0. So I initialize all the variables. Okay. So n 0, estimate 0 and error 1. Okay. And because I have to initialize those variables, because I use those variables in my conditions. Okay. Okay, in the loop. Okay. So that's why I have to initialize all these variables, okay, to start with. Okay. and I use such that my these conditions are all valid. Okay. Otherwise, this loop is not performed anymore. Okay. It is not started or did not start. Okay. So, if we let us say put error is 0.001, that is not this conditions. Okay. Right. Then this loop is not start. Right. Okay. So, so this is n 0 and I initialize this, and while the conditions are basically n should be less than this number. Okay. So, that means, so I update n. Okay. And basically I increase n 1 units. Okay. But n should be less than this. Okay. And error is greater than 0.001. When the error is less than this loop stop. Okay. Because I reach the accuracy. Okay. I want the accuracy is this level. So, that is why I always perform the loop when my error is greater than this. Okay. If the error is less than these numbers, that means I reach the accuracies at this level. So, I stop. And every time I generate x is a real numbers, okay, random numbers. Okay. So, this means I generate random numbers in between 0 and 1. Okay. So, if we do not put anything within the third bracket, so that means they generate a number within 0 and 1. Okay. And I calculate this estimate. So, my estimate is basically estimate equals to estimate times n plus x square over n plus 1. Okay. And I calculate the error is basically the absolute values of this estimate minus 1/3. Okay. And then I perform n plus plus. So, that means if I start with n equals to 0, n plus plus means that n equals to n plus 1. So, now my n is 1. Okay. And then perform again loop again. Okay. So, n equals to 1 and then start from the beginning. Okay. So, stop when enough samples are generated, that means I have a limitations on the samples, let us say 10 to the power 5. Okay, I put here. So, if they reach 10 to the power 5 or the accuracy is reached, okay, because this is a random number. So, this is not a conditions. Okay. I just generate some numbers. Okay. Okay, so, this loop stops if these two conditions are filled. Okay. So, I reach enough sampling, okay, or I reach the accuracies. And this is a typical Monte Carlo stopping criteria. Okay. So, how to stop your Monte Carlo simulation? Basically, I stop the number of samples, okay, or I stop the accuracies. Okay. And this randomness generated basically x belongs to 0 to 1, uniformly they generate in between any numbers. Okay. Because I do not put yeah, I do not use any limit here. Okay. So, by default they choose 0 to 1. Okay. If we just put this up. So, in these examples I basically calculate the so this definite integral. Okay. So, I want to calculate 0 to 1 x square dx. Okay. So, that is why, so my limit is basically 0 to 1. So, I generate random numbers within that range, okay, 0 to 1. Okay. So, my x is 0 to 1, any numbers, okay, I generate, okay, and I generate many times. How many times? I generate this times, okay, at most. Or if I reach the accuracies within below these numbers, then it is fine. Okay. I am not generating this large samples. Okay. So, let us see, okay, because if I reach the accuracy, because I want to also want some accuracies, okay, in my results. Okay. So, so what is the estimate is then? How to calculate this this integrals, okay, definite integrals. So, my estimates are basically this x square. So, I can write this integral into a sum. Okay. Right. So, basically I calculate this. Okay. So, sum over x square over n, okay, and where x is basically x I. So, I generate let us say n numbers, okay, and I calculate the square of these numbers and then sum, okay, and divided by the total numbers. Okay. But my n are basically varying. Okay. Let us first I generate one sample. So, n equals to 1, I calculate x square over n. Okay. for the x are basically in between 0 to 1, okay, and I increase n, okay, every time. So let us say I have a 10 sample. So my n max is 10 and the samples are basically I generate 10 0 to 1 with n max and I calculate sample square, right, because I want to calculate x square. Okay. So if we do this, so these are the numbers, 10 numbers, okay, where we calculate all of the basically square of the samples. Okay. So samples is a list. Okay. So if you just see your sample is a list, okay, within 0 to 1, okay, and your values are basically sample square. So if you square all of these numbers, okay, you get this one. But I have to calculate this, the sum over this number, right, all these numbers and divided by n for every n, right. Okay. So that is why I calculate the accumulate things. Okay. So accumulate values is basically, so for this case there is only one number, so this divided by 10. Okay. So if you just run this, so you see this divided by your n max. So n max is for one case 1, right, because this is 1, right, this is 2, n equals to 1 here, right. So accumulate the values. So values are basically 1, 2, 3, 4, I have 10 values, okay, that is sample square. Now my first one is n equals to 1, right, and my values is this, okay. So this is basically this divided by 1, that is why it is. For second case, let us say it becomes clear if we start with 2, okay. So I have 2 numbers and then I calculate estimates this, yeah. So we see, so your first case, this is your values, okay, and n max 1 and I accumulate this only one numbers that actually return this exactly the same numbers, okay. And second case, I calculate the sum of these two numbers, okay, because this is that the accumulates actually. So if we calculate the sum of these two, right, and then I divided by 2, right, because I have 2 numbers, okay. Okay. So sum of these 2 and divided by 2, you see 0.1 that is actually this number. So let us say I generate 3 samples, so 3 and I calculate the accumulate. Again you will just check the first one remains same as it is, okay. So 0.50799, 0.507922, okay, exactly the same numbers because you just divided this number by 1, okay, that is why this. But the second case we just add the first 2 numbers and divided by 2. So add first 2 numbers, okay, and divided by 2. So this is actually this. So 0.20722, 0.20722. Third number basically we add these 3 divided by 3, right. So we add these 3 numbers and divided by 3, that divided by 3. So you see 0.219657, exactly. So in this way it goes also. So my estimates are basically calculate these numbers, okay, repeatedly. So up to what n, we basically sum of all the previous up to this n, okay, and we divided by n. So, okay. So for every n I calculate this, okay, right. So this is my estimates here. Okay. And you can also write in this very simple form or compact form. Okay. So it is basically your estimate is the previous estimate times n plus x square over n plus 1. So, if you just do a simple algebra, you can also write this I plus 1th term in terms of ith term. Okay. So, this is the recursion relations. Okay. So, you calculate from the previous estimate how to calculate the new estimates. Okay. So, we just basically add x square terms and divided by n plus 1 to the nth term. Okay. So, that is basically, so this is your nth estimates and then you multiply it by n plus x square divided by n plus 1. This is your nth plus 1 estimate. So you can easily calculate from this. Okay. So this recursion relations. Okay. And your error is basically, this is your estimates, and your true value are basically actual value, is 1/3, right. So if you just perform an integral, okay, so let us do an integrate. So this is basically so ni integrate, right, and I have to integrate x square from x 0 to 1. Okay, you see 1/3, right. So this is 0.333. So this is 1/3. Okay, I have to perform in numerical integrations because this is a definite integral. Okay, so this is 1/3, right. So that's why I subtract the 1/3 value here, and this is my error. Okay. And this error, if this error is less than 0.001, this loop is stop. Okay. So if we run this, okay, and let's see what is the estimate and where it stop. Okay, I think this is, we can run again, and then yeah. So your estimate is 0.332385 and n is 969, right. So that means at 969 times you generate the random numbers and they do not achieve this accuracy. Okay, but at 969 steps, okay, you reach this accuracy. So because this is not reached yet. Okay, so that means the error is reached. Okay. So if you calculate the error, okay, so you just subtract from this to this. Okay, you see that the difference is basically at this level. Okay. Right. So at 969 it stops. Okay, but my in I have to, yeah. So this is very large numbers. Okay, I put by default much below that they actually reach this accuracy. So in this way you can calculate the values of the definite integrals. Okay, using just random number generations. I will show more examples, okay, later on. Okay, I hope it's clear. Now if you plot this, okay, how if you see that how this number actually converges to your true value. Okay, so let's see. So if we plot this, sorry, I think there is estimate and yeah. So estimate is a number, right. So that's why I have to use, let's say I have a 100 samples. Yeah, let's say I have 1,000 how many, let's say 10,000 samples, and I calculate this or hide this, and then I calculate estimates, okay, and then I have to plot this. Okay, so you see, so it converges at so initially they fluctuate, but at the end they converge to a number that is very close to 0.333. Okay, so you see, so initially they fluctuate, right. So start from very large number and then fluctuate up and downs, and then actually converges to some numbers. Okay, at the number of samples that goes on. So I choose 10,000. So if you increase more, and that actually already this is converged, okay, to a number. Okay. So now if you do, let's say, constant array, so it's basically this. So you can see. So yeah, so you can see. I just put the plot range. So 0.2 to 0.4, right. So within that, so 0.5. okay, so 0.3 to 0.4, let's 0.3 to 0.4. This is zoom in version, so you see. Okay, so initially they fluctuate, but at the end they almost converge. Okay, the error is small. Okay. So this is your actual values. Okay. The red line, okay, straight lines, the exact value 1/3, and this is the Monte Carlo estimate, the blue one. Okay. So you see that how this this converges, okay, when we increase the number of samples. Yeah, so the error is basically decreases approximately 1 over square root of n. So n is basically total number of samples. So here I use 10,000. So if we just calculate the errors, it is basically 1 over square root of 10,000. So this is statistical results. Okay, so you can derive explicitly that your error in this Monte Carlo simulations are basically 1 over square root of n. Okay, goes as 1 over square root of n. Okay. So yes, so this is the accumulate thing. So I already told that how this accumulate works. So if we just do a quick example, is that, so in first case is 1, so that goes to 1. Okay, the second case they basically add the first two terms. Okay. So 1 plus 2 is 3, and the third case is basically add 3 terms. So 1, 2, 3, so it's 6, right? So and so on. This is the accumulate functions actually too. So this is basically accumulate, so cumulative sum. Okay. Okay, all right. So now I'm going to discuss the randomness. Okay. So in Monte Carlo, we use the mean of random samples to find the value we do not know. Right. So let's say I estimate pi. Okay, throwing a dart at a square containing circle. So this is very good way to estimate pi. Okay, using just random darts. So how to do that? So that is very nice example. So let's say I use 10,000 samples, okay, sample points or sample darts. Okay. So I generate points, okay, that is 2D points. Okay. So this means that I generate -1 to 1, okay, and n comma 2. That means I generate 2 points at a time. Okay. And so basically I generate 2 points at a time. That means I generate a points lie in the square -1 to 1 and -1 to 1, right? So you understand, right? So this is square is a unit square, okay, where the center is at 0. Okay. So I both x axis might run from -1 to 1, y axis run from -1 to 1. Okay. And I draw a complete square, okay, and I generate some point in the square. So that means they have a x coordinate, they have a y coordinate, right? So that's why I generate 2 points simultaneously. Okay. Basically, I generate 1 points in 2D. Okay. So if you generate 2 points simultaneously, that means you generate 1 points in 2D plane. Okay. They have a x coordinate, they have a y coordinate. Okay. And you repeat these things 10,000 times. So basically, you generate 10,000 x coordinate, 10,000 y coordinate, okay. Right? That is the mean. Okay. So your points is basically 1 point in the 2D plane, okay. And inside Q. Okay. So inside Q is basically this is a unit step and 1 minus total point square comma 2. So what does this mean? Okay. So let's break this. Okay. So let first, so this unit step is basically a step functions, okay, and 1 minus this total point square comma 2. I am coming to this point. What does this mean? So this is basically 1 minus x square plus y square. Okay. So this quantity tell us whether a point inside the unit circle or not, because we have a square and we draw a circle of radius 1 inside the square. Okay. Okay. And now I calculate the quantities. So 1, so this is area of the square, and minus x square plus y square. Okay. And if this is greater than 0, that means your point lie outside the circle but inside the square. Okay. or if it is less than 0, that means your points are inside the circle. Okay. So, that is why I use a step function. Okay. So, that it returns 1 or 0. If it is returns 1, that means the point inside the circle. If it returns 0, that means the point outside the circle. So, this step function is greater than 0 or less than 0, right. So, the variable in the step function is the unit step, and now this one is the variable, let us say. Okay. So, I calculate this number. If this is greater than 0, they return 1. If this is if this is less than 0, that means my points are inside the circle. So, they return 1. Okay. If this is greater than 0, they return 0. Okay. So, let us do an example. So, let us say I have a points, okay, 0.3, 0.4 x coordinate, y coordinate. I have another points 0.9, 0.7 x coordinate and y coordinate. Okay. And I calculate 0.1 square, that means they square every number in this array. Okay. And I calculate total 0.1 square comma 2. What does this mean? This means I calculate total of this. So, this is basically x y, okay, and this is also x y. So, this is let us say x 1, y 1, x 2, y 2. Now, I square this. So, that means they return. So, let us see. So, they return x 1 square, x 2 square. So, we just do this. So, 0.3 square, 0.09, 0.4 square, 0.16, and 0.9 square, 0.81, 0.7 square, 0.49. Okay. And this total is basically I add these two numbers, right, within one array, right. So, 0.09, 0.16, 0.25, 0.81, 0.49, 1.3, right. So, basically I calculate this number x square plus y square, okay, for each pair of x y. Okay. So, this is the thing. So, for each point, okay, I calculate this 1 minus x square plus y square, okay, and I use a step functions, okay, to determine this whether it is the point inside the circle or the outside the circle. So, that is why I choose inside Q. That means, if the point inside the circle, so this return 1, okay, that means this is inside Q. So, my inside Q is a counter, okay. So, I count this, okay. Now, I count how many darts hit the circle, that means how many darts inside the circle, okay. This is basically total inside Q, right. So, basically I add this numbers, okay. Okay. So, this is basically some logical state. If you perform this logical state, that means my points are inside. Now, I calculate how many times this is happened. So, that is the total inside Q, okay. And my estimates pi are basically 4 times the total number of darts inside the circles over the total number of darts I throw randomly. Okay. So, if you do this, you see, so you get 3.132. Okay. What is the values of pi? So, if you calculate the values of pi, it's n, it's pi. So, it's 3.14159. So, it's accurate up to second digit. Okay. So, now if you calculate also how many points are inside, how many points are outside. So, we just select points, okay, and this is your first coordinate and this is your second y coordinate. Okay. So, x square plus y square less than equals to 1, that means this is inside. If these conditions, so if these numbers are greater than 1, that means this is outside. So, I select from all the points how many points are outside, how many points are inside, and I plot this. Okay. So, my inside points are blue and outside points are red. Okay. So, I do a list plots and I show in one graphic on thing, and I also draw some circle, okay, and you see all the blue points are inside the circle and all the red points are the outside the circle, okay. But all the points are generated in this square -1 to 1. Okay. So, this is actually, I mean, this is from the graphics, yeah, so this is basically from your plot size. Okay. So, that is why this is looks like a rectangle, but it is actually square. Okay. So, if you just see the number -1 to +1 and yeah, so if you just see -1 to +1, also -1 to +1, because my this plot size at the rectangle, that's why it's so a rectangle, but this is actually a circle. Okay, and all the red points are basically outside the circle. So here I use the equality conditions are also inside, so that means the boundaries are also counted as inside. Okay. So yeah, blue points are at the inside the circles, and the red points are the outside the circles. Okay. So you can do a quick simulators to do that. Okay, to calculate the pi and how this number achieves. Okay, how this pi values actually achieves if we throw random dart, okay, within the square, and then calculate the probabilities of getting the darts inside the circles. Okay. So if we do this, I use a dynamic module. Okay, so yeah, so in my dynamic modules, so there is a points I throw, and inside I calculate how many points are inside the circles, and this is the total number of points I throw, and this is the running. So I how long I run the simulations. Okay, and this is the points, and this is estimate pi. Okay, so these points I generates. Okay, and I randomly generates 1 points at a time, and these points are basically a list. Okay, so I add to this list. Okay, so this is PTS the basically, yeah, so basically it's a variables to generate the numbers. Okay, and this is my list. Okay. I list to this. Okay, so basically I do a column, okay, where I put this dynamic thing running, stop, and start bottom. Okay, and this running when equals to is not running. Okay. So if this is true, then these things are goes on. So the dynamic things. So if the running is true, okay, that means if we put stop, that means it stops. So this is the running, and the first conditions is a stop. Okay. Okay. So this is true. If this is the case, then this goes on. If the conditions are true, then this is stop. Okay. Otherwise, start. Okay. Okay. So this is the if conditions. Okay. So if running is true, okay, that means if it start, okay, and I put the running actually not running. Okay. So if the running starts, so we randomly generate 1 points from this -1 to 1. Okay. I have generate at a time 2 points. Okay, x and y coordinate. Okay, x coordinate and y coordinate. Okay, within this -1 to 1, and this is my points, and I append to this list. Okay, points list. Okay, so I append to this. Okay, so this is an empty list. Okay, I start with an empty list. Okay, so first generate one xy coordinate to this list. Okay, and I add total plus plus. So go to next one. Okay, and my if this points 1, the first coordinate in the points, and the second coordinate, that means the y coordinate. Okay, so x coordinate is the first one, and the y coordinate the second one. If we calculate this and it is less than 1, that means I have another counter inside. So inside plus plus. So that means inside actually is a counter that is count how many points are inside. Okay, and this total plus counter is basically count how many points, total number of points. And my estimates pi is basically 4 times how many points are inside, okay, divided by how many the total number of points. Okay, and you do repeatedly times, okay, until this things are not stop. Okay, until this running is not false. Okay. So that means if we don't put a stop bottoms, okay, it basically goes on. So, okay, so there is no other conditions here, okay, to stop these dynamic things. Okay. So now I show the things, okay, in that. So basically I have to show this the graphics, okay, where I yeah, so first I generate rectangles, okay, and I also draw a circle, okay, with a center 0 and radius 1. Okay, so center at 0 0 and radius is 1, and I generate a rectangle minus 1 to 1 and also 1 to 1. Okay, so basically minus 1 1 and 2 1, so generate a rectangle. Okay. So basically a square. Okay. And yeah, so now I denote the points that is inside the circle by blue, okay, and if the points outside the circle is basically red. Okay. So basically we generate random points, okay, so PTS, and append to these points. Okay. If these points if these conditions are holds, they denoted by blue. If these conditions is not hold or the other conditions are hold, is basically greater than 1, that actually denoted by red. Okay. And I also have my plot range are basically this, and image size is this, and I update my interval is basically 0.03 second. Okay. So so once you do a simulation, so we have to put a time intervals, okay, when the next points are generated. Okay. So my intervals are basically 0.03 second. Okay. And I also print these numbers, okay, how many total dots are there, okay, and how many number of points are inside, and the estimated y, okay, every time. So this is dynamically I have to see. So now I have to run the simulation. So let's start with this. Sorry. Okay, so let's run this, okay, and you will see. Okay. Okay, you see there is some reminders. Okay, so I have increased size a bit. Okay, so now you see that I have to play the start bottom. Okay, but once you put a start bottom, okay, so you see that the total number of dots actually 0. Okay, and inside the circle is 0, estimate pi is 0. Right? Now I see now I put yeah, so now I play the start bottom. Okay, let's see, okay, how these things are that. So right, so dots are basically increasing. So can you see the estimated pi is 0.15, your true value is 3.14. Okay, you see that how this fluctuates. So you put a more dots. Okay, if the dots inside the circle they blue, and if outside the circle is red. Okay, so total dots is this, and inside circle is this, you see. Okay, how the number, okay, changes. Okay. So you see 3.14 you already achieved, okay, in this number of events. So you create more and more, is also fluctuates, okay, until you reach 10 to the power 5 or 6, they almost convert. So this pi is very interesting. I mean, if you calculate the probability, okay, of the random point landing in the circle is basically pi by 4. That means if we calculate the fraction, right, how many points inside over the total number of points is basically the probability, and if you multiply it 4 times this, you get a you get the values of pi, right. So that is geometrical interpretations, okay, how to estimate the values of pi, okay, from this. For this Monte Carlo simulations, the prime examples. Okay. Now we see basically if we you see that this is basically fluctuates. Okay. So total number of dots are increasing, but you are basically away from the true value. Okay. So that means we need more time to converge, or more number of points. Okay. We need to calculate, okay, these things to minimize the error. Okay. Okay, so you almost achieve up to 4 significant digits, right? At this, okay. So I stop this. Okay. So this is the dynamic way we can check that, okay, how this number actually achieved by throwing random darts. Yeah, so the behind physics is basically this. Okay. So we calculate the probabilities, okay, of a random points landing in the circle. This is basically pi by 4. So we multiply this probability times this number 4. So basically the values of pi we get. So if you also draw a if you plot a running means, okay, how this number actually achieved, okay. So I calculate again similarly. So the 4 times the accumulated inside Q over range n, okay, just like before. Okay. So I calculate how many points are inside and I sum of the basically cumulative sum if we perform. Okay. So this is basically running means. Okay. If we increase n, more n and n, we calculate at every n I calculate those things. Okay. So this is running means I calculate this, and if you plot this, okay, so this is basically this. So you see. So if you increase n and n and up to 10,000, so it is the values, okay, actual. So this if you zoom this, yeah, you see that this line solid gray lines are basically the absolute values, and you see that how we reach this to the absolute values, okay, by increasing the iterations. Okay. Okay, so these accumulate functions I use here to calculate the cumulative sum, and I calculate the means for every n. Okay, and increasing more n and n. So basically, I calculate this is a running. Okay. Okay, so this is, let's run 1000 Monte Carlo experiments, where each experiment throw 500 random darts in the square. So I perform a simulations, okay, where I perform 1000 experiments, okay, and each experiments, okay, I perform 500 random darts in the square, okay, and I calculate the mean of these each experiments and draw a histogram plots, okay, for all this number of experiments. So basically, my number of simulations times are thousands, okay, and my number of darts are 500 in each simulations. Okay. So the simulations are basically table. So I create a table, okay, where I generate the points, okay, -1 to 1 number of darts. So 500 darts I generate with at a time 2, right. So basically x and y. Okay. So this is my points, okay, and I calculate how many points are inside. So it's basically I count the point, okay, where my points are p. So this is put any number, any variable here, okay, and such that my x coordinate of these points and y coordinate of these points, and if we calculate the square of this and then sum, that should be less than 1. Okay. If this conditions is true, so these points is basically count as 1. Okay. So this is a pointer. So from first we generate a points, okay, from this random, using this random real, okay, I generate x y coordinate, okay, and I check that, okay, for this point if these conditions hold or not. Okay. If these conditions hold, okay, for these points, okay, I count my inside is a counter, so my inside is 1, okay, and again this is inside is 2, okay. So it repeatedly goes on if these conditions are true, okay, such that. So this is means the such that, okay. So my points, and I use this pointer p, okay, such that the first coordinate and square and the plus the y coordinate square, okay, x square plus y square is less than equals to 1. So I count this 1 in my inside counter, okay. So this is the count functions too, okay. Again you can also check by doing some individual running, and then I calculate my tables are basically this. So I calculate 4 times how many points are inside divided by total number of darts, okay, and comma n simulations, okay. So this is my tables, okay. So, first in the first columns I put these numbers, and the second one is the number of simulations. Okay. So, if you have 1 simulations, what is the values of these? Okay. Right, because in each simulations, okay, I throw 500 darts, okay, and I do these experiments 1000 times. Okay. So, basically I make a table, okay, where my simulations numbers, let us say in one column, okay, 1, 2, 3, 4 simulations, and I calculate what is the values of pi from first simulations, from second simulations, because each simulations I throw 500 darts, okay, and I calculate to estimate pi. Okay. Basically, how many points are inside and how many points are total number of points. So, total number of darts is always 500. So, I just calculate how many points are inside, okay, from this 500 darts for one simulation. Okay. So, for one simulations I calculate how many points are inside the circle. Okay. So, this is basically 4 times, and I just multiplied by 4 to get the values of pi. Okay. Okay. And I make a list of the number of simulations and the values of pi. For each simulations you are getting the different values of pi. Okay. Now, I calculate what is the mean values of this, okay, and what is the sigma, the standard deviation. So, we calculate this mean and sigma, and now I show the histogram plots. Okay. Okay. So, histogram plots basically shows that how many times you get a numbers. Okay. So, basically I choose a bin size. Okay. So, my bin size are basically so here I create a 30 bin. Okay. So, what is the range of the value estimated pi I get? I just divided into a 30 bins. Okay. Okay, and I have, so I use a PDF. So, this is basically normalize the things. Okay. And I also plot some distributions, normal distributions with this mean and sigma. Okay. Okay. And that run from my minimum values of these simulations and the maximum values of the simulations. Okay. That means the minimum values of pi to maximum values of pi that I got from these simulations. Okay. Simulations table. Okay. So, you see that this is a simulation, that all things. So, now if you do this, so this is the thing. So, that means you see, so this is the probability density. So, this normalized to some scale. Okay. So, they normalized. Okay. And you see that this 3.1 and 3.2 in between, then we are basically getting the number, the values of pi from 3.1 to 3.2, okay, most of the times, because here the histograms are basically the densities are large, right. And if you draw a normal distributions with this mean and sigma, mean values and sigma values, okay, so you see exactly. So, it is nicely bell shaped curve, okay, Gaussian things. Okay. So, where the mean is basically, we calculate the mean. So, let us so this mean is basically 3.14142, right. So, what is the values of pi? So, so values of pi is 3.14159. So, it is very close to this number, right, and the sigma is also very small, right. So, that means by doing these experiments, okay, actually get a better values of pi. Okay. Right. So, if you increase this number of simulations to 10,000, okay. So, it takes some time, but yeah. So, you see, so it basically more converts to absolute values. Okay. Let us check what is the mean and what is the standard deviations. Just for compare, I choose a different. So, you see 3.142, it is now changes again, okay. But yeah, so now I have to increase more. Okay. So, let us say I increase 10,000, but I increase the number of darts to be 5,000. Yeah, now I calculate this mean and standard deviations. Yeah, my sigma is very small. So, you see, is compared to that, now my sigma is very small. So, it's very far things, okay, there, and your mean is 3.14109. So, your true values are basically 3.14159. Okay. So, if you compare this one is good, but this is large standard deviations. So, in this case you have small standard deviations, but mean is somewhat slightly shifted away from the true value, okay, in compared to this. But yeah, I mean, this is a little fluctuators is here and there, but you are basically getting if you do increase the number of samples of the darts, okay, you can reach to the absolute true values, okay, close to the true values. Okay. So, okay, so here is the count is basically these functions I use here to count how many points are inside is there. So, it is basically I have a list, okay, from this list if the condition is satisfied, so I count this. Okay. So, it counts how many elements in the list satisfy the conditions. Okay. So, that's why I use count here, okay, right, because this points is basically I have how many points now, 5,000 points here, right, with it each of have a two numbers x and y, and from these points, so this is basically a list, okay, and I use these conditions. If this condition is true, then this is count. So, that means inside I basically count how many points among this list, okay, are basically satisfy these conditions. Okay. So, this is actually we use. So, Monte Carlo, then the Monte Carlo estimate basically clustered around the true value. Okay. So, you see, so your estimates are from each sample for each simulations, okay. So, I getting different the values of pi, the estimated pi, that is differ from that, but it's actually clustering around the true values, okay. And my shape is basically Gaussian like, okay. So, the distributions are the Gaussian like distributions, okay. We have some mean and variance, okay, standard deviations, okay. Okay. So, that is basically clustering with the Gaussian like distributions. Okay. So, now we do more realistic examples, okay. Let us do another example using Monte Carlo methods. So, in these examples I basically discuss geometrical Brownian motions model. So, we simulate a future stock price path using Monte Carlo simulations. So, let us assume the stock price are assumed to follow this model, okay, geometric Brownian motions model. Okay. So, where the ST is basically my simulated price at some time t, and we start with S0. Okay. So, this is my initial price, okay, and this is my simulated price using this model GBM, okay, and according to these models my simulated price at some time let us say t, okay, capital time t, and this is basically S0 from initial time initial price times exponential mu minus sigma square over 2 times t plus sigma times WT. Okay. So, where mu is the basically drift, the expected annual return, okay, and sigma is the volatility. Okay. So, volatility, that is basically standard deviations of the returns. Okay. So, we have a some let us say we have some mean, this mu and sigma is the standard deviations, and t is the time, okay, and again I have a WT. So, this is the time horizon, you can express in years. Okay. So, let us say in 1 year, so I put 1, okay, and my WT is basically the Brownian motion. So, this is a random part I put there, okay, and it follows some Gaussian distributions with a mean 0 and the variance t. Okay. So, let us say I have a 1 year. So, my variance 1 and mean 0, I basically put some random distributions, normal distributions, okay, Gaussian distributions, okay, and put a random numbers. Okay. So, this is basically some random part that add to this things and we add exponential. Okay. So, this is the according to this Brownian motions, geometric Brownian motions models, your estimate price at your estimate price at that time t. Okay. Okay, so let's do this. Okay, so let's perform a simulations. Okay, based on this formula. Okay. So I initialize this all this number S0 mu parameters. Okay, sigma and t. Okay, and also the steps. Okay, so steps basically. So I calculate when. So I calculate basically at every day. Okay. What is my update? So I start with S0 100, okay, starting price, and my mu is 0.05, that is expected return, that means 5% I have a return. Okay. So 0.05, so 5%, and my sigma is 0.t. Okay, so standard deviations, and let's say in 1 year, and I use step is 252. That means in 1 year, so there is a 252 working days. So that means I have a trading days 252, right. So that means I calculate daily. Okay. And yeah, so basically then I basically use this formula, okay, to calculate ST, okay, daily. Okay. So I update this daily. So that's why I use S0 times exponential, okay, times exponential. Now I have a mu minus sigma square over 2 times t. So this is basically I accumulate those things, okay, and I generate a random numbers from these distributions. Okay, so this is basically normal distributions, okay, with mu minus sigma square times t over steps, right. So you see this, in this case I use instead of t I use t over steps. Okay, that means I calculate daily. Okay, so my delta t. So each step correspond to delta t, that is our t over steps, total number of steps. I use 252 and in 1 year, right. So this is my time increment. Okay, that means my model evolves daily. Okay, and this random variate normal distribution physically generate 252. Okay, so you see this is steps to I generate 252 random numbers. Okay. And I calculate accumulate. Okay. So that means I compute the cumulative sum of these random returns. Okay. Right. Okay. Okay, and I use this delta t, that means my, so this basically represent my daily log returns. Okay, and I generate 252 times. So this is my steps. So I already use steps here 252. Okay, and this is my price path. Okay, now I plot this. Okay, and I generate the path for 50 possible future stock trajectories, right. So we start with 100 S0, and what is the values of S, and let's first generate only 1. Okay. So my path for one possible trajectory, okay, and I plot this. Okay, so this is my trajectory. So I start with the hundreds, and there is up and downs, and ultimately at the end of year, okay, I get this number. So 252, you see that. So this now I see, let's say I generate 50. Okay, because let's generate 50 possible future stock trajectories where each path represent one possible future. So this is one possible future of the stock. Okay, and I generate 50 similar. Okay, let's see. So if we generate this, you see this is highly scattered. Okay, so you cannot predict. Okay, because if one predictions goes down and the other predictions goes up. Okay. So in this way, I mean everywhere is there. Okay. They have this. Okay. So you cannot predict. So this many random curves are diverging over time, and that is actually your financial risks. Okay, in this models. Okay. But the average rates actually follow the drift. Okay. But but you see that this some curves are going down, but the some curves are going up. Okay. So, we cannot predict accurately, but yeah. So, you see okay, how this changes okay, from one path to another. So, this is where I use a random number to do that things. We can also do in the particle diffusion simulation. So, these models so how a particle moves in a randomly 2D space similar to the Brownian motion. Sorry. So, basically I generate minus 1 to 1 have 1,000 points okay, in the 2D plane. So, okay, and I accumulate this. So, this is my work. So, in let us say I have a 2 points. So, that means I calculate 1 and then I sum to the second point. So, in this way I go the goes on. So, the accumulate functions are goes on. So, my work path are basically these. Okay. So, I generate random steps for a particle in 2D space and I calculate the cumulative sum of this. So, that is my trajectory, that is my work path. Okay. So, let us plot the particle path. So, if you plot this, so I plot my line plot okay, for the work and I also put the point okay, indicate what is my first point with a red point and what is my last point with a green point. So, and the particle paths are basically the blue line. Okay. So, if we see, so we start from here from the red point okay, and this goes on and we end it here in the 1,000 samples. Okay. So, this is basically some particle diffusion path. So, if we start from here and how it diffuse to in this space. Okay. So, it is basically how the particles the gas particles are basically moves okay, the particle simulations, particle diffusion simulations okay, where the blue lines are basically path of the particles and the red point the starting points and the green point are the final positions. Okay. So, now I discuss the Monte Carlo simulations for error propagations. Okay. So, instead of using calculus of the derivatives okay, we perform an experiments too many times to calculate to see how the distributions of a result behaves. Okay. So, these things I discuss in the lecture 3 okay, for the data analysis lecture. So, I request you to go back to the lecture 3 and see there. Okay. So, I am not discussing this because I do not have time to discuss this today. So, yeah, so I encourage you to go to the lecture 3 and yeah yeah learn from there. Okay. If you have any questions, you just drop me an email or you can put the questions in the forums. So, let us do some problem. Okay. So, that is closely related to your assignment problems in the next couple of minutes. So, let us first the problem, that is how to find the integrals. Okay. So, my integral is basically I equals to 0 to 1 on over x to the power 4 dx okay, using Monte Carlo methods. So, I already discussed that in the beginning that how do you perform integrations okay, using Monte Carlo methods or using Monte Carlo simulations. So, here my functions are basically 1 over 1 plus x to the power 4. So, first I define the functions. Okay. So, this is f of x is 1 over 1 plus x to the power 4 and I generate let us say 10 to the power 6 sample okay, and I calculate okay. So, I generate 10 to the power 6 samples okay, within this 0 to 1 because my boundaries are 0 to 1. So, I calculate a definite integrals for the range is basically 0 to 1. That is why I generate 10 to the power 6 points okay, within this range okay, 0 to 1. So, that is my random samples between 0 to 1. So, I generate this and I calculate estimates integral is basically the mean values of this. Okay. So, the mean values of the functions f where this is the x x. Okay. So, this is basically mapped to okay. I calculate f at this points okay, and I calculate the mean. Okay. Okay, I think somewhere defined. Okay, x. Let's quit these things. Because in somewhere we define x, okay, so that's why it's problem. But yeah. Okay, somewhere we define f. Okay, so I quit these things and then I run again. Yeah, so this is the results. Okay, 0.866784. If we perform, if we compile again, so it gets different. Okay, 0.867. Okay, compile again. 0.866. Okay. So how we calculate these integrations? Okay, using Monte Carlo method. So Monte Carlo actually replace the integral, okay, by the average values of the functions, okay, over random points in the integrations region. So let's say I want to calculate or find the values of the integrals, the definite integrals, where a to b fx dx. Okay. So you can approximately write this is basically proportional to b minus a times 1 over n and sum over I goes to 1 over n f of x I. So basically I generate n number of points, okay, and I calculate at every point what is the values of the functions, okay, f of x I, okay, and I calculate sum of these, okay, and I divide it by n, okay, and that multiplied b minus a. So in this case I have a so I have yeah, so in this case we have a equals to 0, b equals to 1. So that means this b minus a is basically actually 1, right. So that's why I am not multiplying anything here, okay. And I calculate the mean values of this. This is basically the mean values of the functions, right. So I calculate the mean values of the functions f, okay, where my points are basically those x's. So you can using this shortcut you can calculate the values of the functions, okay. So this is basically I calculate the values of the functions at these points and then I calculate mean, okay, basically this I calculate this, okay. So this is my estimate integrals, and if you calculate what is the actual values of these integrations using this ni integrate functions, so this is your actual values, okay. Okay, and now we compare, okay. So up to 4th decimal place, okay. The accuracy is actually in 3rd decimal place, okay, up to 3rd decimal place, okay. So in this way so you just check that if we use, let's say 10 numbers, okay, 100 numbers, okay, okay, you see it's differ, right, it's differ actually at 2nd decimal place. If we increase more numbers 10 to the power 7, so it takes some time because 10 to the power 7 is too large. So you see 8, 6, 7. So 3rd decimal place 10 to the power 6 is what. Yeah. So in this way you can calculate the values of the integral using Monte Carlo method. Okay. Let's do another problem. So draw a random numbers from a uniform distributions on 0 to 1. Okay, and keep adding them until their sum exceed 1. So basically at every time you draw a number, okay, random number from these distributions 0 to 1 and keep adding them. So first I generate one number and then I generate second number and I basically add this such that my numbers are sum is basically less than 1, okay, or not less than equals to 1, not exceed 1, okay. And let J be the number random variables, okay, is required, and for the sum is to exceed 1, right, and repeat this experiment 10,000 times and estimate the mean values of J using Monte Carlo simulations. So, you getting my points? So, it is clear what is the question is, right. So first part you understand, right. So it's clear, right. So basically I generate random numbers, okay, from these distributions I add them, okay, right. So let's say I generate first number x1 and then I generate second number. So I basically I calculate x1 plus x2 plus dot dot xn, okay, and that denoted let's say Sn, okay. And my condition is Sn where my sum over, so the sum Sn is always less than 1, less than equals to 1. Okay. If it is greater than 1, then it's stop. Okay. And this xi is the number of random variables required for the sum to exceed 1, right. So, let us say in first case I need 3 numbers, okay, because if we yeah, so beyond 3 my sum is exceed 1. Okay. Right. So, this xi is basically how many number of how many random variables required for the sum to exceed 1. Okay. Right. So, this is my counter is basically xi. Okay. And I repeat this experiment 10,000 times, okay, and I get different values of xi for each experiment. Right. Now, what is the mean values of xi? Right. Similarly to the pi estimate, right. So, I calculate, so I throw 500 darts, okay, in one experiment. I calculate the values of pi, right, and I do the same thing in a 10,000 times. So, in each simulations I calculate the values of pi, and that is different from this, and I can then from this I calculate what is the mean values of pi, what is the standard deviations, right. So, we do the same thing here, right. So, we generate random number from 0 to 1, okay, and we add them, okay, until their sum exceed 1s, okay, and I calculate, okay, how many random variables are required to actually get this. Okay. So, that is my xi for one experiment. Let us say in my first experiments I need only 2 numbers to get 1, right. Okay, it happens. Okay. It is a random number, right. So, second case it is my 4, 5. Okay. So, I calculate the mean values of xi using this Monte Carlo simulations. So, I use a trial module. Okay. So, this is basically I start sum 0 and count 0. So, I perform the loop while my sum is less than a, because this a is a variable. Okay. And I calculate sum is basically sum plus equals to random number. So, basically it is add 1 by 1, and I then calculate my counter is calculate count, how many times I calculate this, okay, how many times I add this. Okay. So, that is they actually count, okay, and they actually return count. Okay. So, this is a counter, okay, and they actually return at the end count, okay, from this module. Okay. So, if we run this, now I do 10,000 times, okay. So, I perform this 10,000 times, okay, and each times I calculate this. So, trial 1, so that means my a is 1. So, this is my sum, okay, not exceed 1, okay. So, sum less than equals to 1. So, I put here 1, and I do a number of times, okay, 10,000 number of times, okay, and I make a tables. That is my simulations, and I calculate estimates the mean values of this, okay, from these histograms. So, you see 2.7189. So, this is actually the values of E. Okay. So, if we calculate this, so this is the values of actually E, because the general result that if we keep adding it adding uniform numbers from this distribution 0 to 1 until their sum exceed 1. So, this is basically the mean values of this variable xi is actually E. So, you can show this, okay, and we actually got that. So, we get that 0.7189, and the values of E actually 2.718. So, up to 4th decimal place. Okay. Yeah, it's basically accuracy is up to 3 decimal place. So, now do another example. So, let us say consider the Jacobian matrix, okay, where the matrix is basically A, B, C, D, where A, B, C, D are the basically Gaussian distributions, okay, with a mean 0, standard deviation 1. Okay. So, this normal is basically Gaussian distribution. So, independent Gaussian random variables, okay, where my A, B, C, D are basically generate some number from this Gaussian distribution. So, and a saddle point occurs when the determinant is negative. So, A D minus B C, if we calculate this, and if this is less than 0, so there is a saddle point, okay, might be, and use a Monte Carlo simulations to estimate the fractions of the matrices that produces saddle points. So, basically I generate random numbers, okay, for A, B, C, D, okay, and I calculate the determinant, okay, and I perform Monte Carlo simulations for this, and I calculate how many how many number of times, okay, I get a saddle point. So, basically I calculate the fractions of matrices that produce a saddle point, that means this determinant of a less than 0. Okay. So, simply basically compute the probability, okay, for AD minus BC less than 0 by random sampling. Okay. So, it is clear. So, I randomly generate the matrices, basically I randomly generate the element of the matrices, okay, from these distributions normal 0 1. So, from the Gaussian distributions with the mean 0 and standard deviation 1, okay, and I calculate the determinant. Okay. So, basically I calculate the probability of this determinant less than 0, right. So, the logic is same, okay, similar to the pi calculations problem. Okay. So, I generate 10,000 sample, where you see that I generate my matrices are basically random variate from these distributions 0, 1 and 4. So, at a time I generate 4 numbers, okay, and I do the same thing 10,000 times. Okay. So, n, 4 basically I generate 4 numbers. Okay. So, this is generated randomly 2 cross 2 matrices in the form A, B, C, D. Okay. So, I generate 4 numbers, that is basically A, B, C, D. Okay. So, this is A, B, C, D, okay, and I calculate determinants. Okay. So, from each this set A, B, C, D, okay, I calculate the determinants. So, it is basically A, D minus B, C. So, the first one, so mats all comma 1, okay, and times 4, fourth one. So, 1 times 4 times 2 times 3 minus 2 times 3. So, this is basically A, D minus B, C, okay, for all these numbers. Okay. For all the matrices I calculate this. Okay. So, this is compute determinants, and now I calculate fractions. So, this is basically now I select from these sets, okay, or from this list, okay, I select which one is the less than 0, okay, and divided by my total n. So, total n should be 10,000, okay, but I just select, okay, how many are less than 0 determinants, okay, okay, and that divided by n. So, that is basically my fraction. So, this is the probability, okay. So, you see the probability is almost 0.5, and that is actually right, because we have a determinant less than 0 or greater than 0. So, your probability is half. So, the probability will be half. You can change the random variable A, B, C, D to be any normal distributions 1, 1. Let us say I now change this to 1 mean and 1 variance, and you do the same thing again. So, I just generate my matrix elements from these distributions 1, 1, okay, and okay, again 0.5, because I calculate A, D minus B, C, right. So, if I calculate A, D minus B, C, so that is the same. If you generate A and D, B, C all are the same type of distributions, okay. So, then the A, D minus B, C are all are the same, right. X and Y are the similar distributions, okay. So, there is no problem. So, whatever your distribution is, so your A, D, the distributions of A, D, product of A, D and the distributions of product of B, C are basically similar. So, because A, B, C, D are drawn from the same distributions. So, that is why this fractions is should be close to half, okay, right. Yeah, so I hope it's clear now, okay, and yeah, so these 3 problems are very close to very similar to your assignment problems. I hope you can easily solve the assignment problems now. Okay, and other problems are already discussed in the previous classes. Okay, so yeah, go back and go back to and repeat the things or do more examples. Yeah, so if you have any questions, you always ask in the forums, or you can feel free to write to me. Okay, so I think it's good time to stop here. Yeah, thank you. Bye bye.